So let's start this new sessions. Okay, session number 9 and 10. So in this particular session we try to explore the solver development in detail. Okay, so let's start this session. So our first solver development is something like this way. Okay, so what we're going to do, we try to incorporate the or try to develop a cavitation transport form. Okay, so that is the idea behind this particular class of solver. So first let's explore few things about the cavitation form. Okay, and then I will explain you what exactly we're going to do in this particular class of tutorial. Okay, so basically the in the OpenFOAM environment, okay, if we see then available cavitation based solver, if we see, okay, so cavitation based solver, if we want to explore in the OpenFOAM area, then we go to the application solver. Okay, let's say multi-phase flow, we have a cavitation form. So let's explore what it is capability. Okay, so cavitation form, transient cavitation code based on homogeneous equilibrium model. Okay, and based on compressibility principle. So that means it is based on the compressible flows or compressibility take into account, and it try to give us the idea. And another solver we have is this interface change form. Okay, so if we explore the interface change form, what it do, solve for two incompressible isothermal immersible fluid with the phase change, okay, using the VOF. Okay, then momentum and other fluid property are of mixture. Okay, and single momentum equation is going to be solved. Set of phase change model is provided. Okay, to and designed to simulate the cavitation, but other mechanism of phase change are supported within this framework. Okay, so here this phase change model is available for cavitation, but other phase change capability also it has. Okay, so what we supposed to do, we adapt the simple framework from this cavitation form, remove the compressibility base concept, and then add up this incompressible base concept here, because this is for incompressible isothermal immersible fluid. So whatever this cavitation models available inside this, it is for incompressible fluid. So that is what we want, because we want to generate the this cavitation form for like an incompressible class of liquid or fluid. Okay, so that is the idea. So let's first explore a couple of the things. Okay, so what we first explore is, let's say, cavitation form. If we look at, okay, so what different governing equation it has inside the cavitation form. So first explore that part. Okay, so inside the cavitation form we have a couple of equations, like one is barometric closure. Okay, so that is the closure available. Okay, and here density, then pressure. Okay, then this psi is the compressibility. Okay, so based on compressibility principle, there is a barometric equation of state is available. Then standard continuity equation, momentum equations. Okay, and rho m are the density of mixture here. Okay, then momentum equations, and then we have a vapor mass fractions, one gamma we are solving. Okay, where this V state is vapor density at a saturation level, and rho else is the liquid density at a saturated level. Okay, so we try to simulate this particular solver or couple of equations with the help of the Pimple algorithm. So that is what we have, okay, inside of it. Okay, and now let's try to look at a couple of its file also, so we have an idea exactly what is coded inside of it. So if you look at the cavitation form, so few things that is available here. This is barometric compressibility model.h, so that is take care of this part. Okay, so that is available there. Okay, so barometric that part is available. Okay, then what else we have extra, we have read thermophysical properties. So that is also we it is try to read the thermophysical properties. Okay, then we have a row equation dot h. So this row equation dot h, what it's going to do, it try to simulate these equations. Okay, then we have a another equation alpha psi dot h. So alpha psi dot h is what going to do, try to calculate the vapor mass fraction. So this equations is try to do. Okay, so row equation try to calculate continuity equation, vapor mass fraction is calculated in the alpha psi, u equation is our momentum equations. Okay, so that is few things we supposed to know, and this is the pimple algorithm. Okay, so now idea is that first when we start developing our this new solver, what we want the all the compressively based dependency we supposed to remove from this area. Okay, so we try to remove couple of the things from this area. Okay, so these things we going to remove. Okay, and then this also not required, so couple of the things we're going to remove, and then couple of the things we try to add up from the interface change form. So let's have a idea about the equation of interface change form. Okay, so interface change form, again it has a continuity equation similar to this. Okay, momentum equations also it has, okay, similar to same momentum equations. Okay, in case of this vapor mass fractions and the barotropic equation of state, it has a transport equation for alpha. Okay, so transport equation for alpha we have, and inside of this transport equation of alpha, okay, so we have a couple of quantities here. One is the on the right hand side RC and RE. Okay, so it is nothing but evaporation and condensation source terms. Okay, and this source term we going to model with the help of the different class of the models. Okay, so that is what we have as alpha equations. Okay, and based on this alpha equation we have a mixture density and the viscosity. Okay, so that is what we have here, and this is the, let's say, this model. If we use some particular model, let's say Kunz model if you want to use, then RC and RE is evaporation source term and condensation source term is coded something like this way. Okay, so this is what we have inside the this interface change form. Okay, so interface change form is nothing but the solver for incompressible fluids. Okay, and it has a phase change along with the interface properties, everything is there. Okay, so let's explore couple of the things inside of it. Interface change, if you look at, okay, so few things we have. This is for the MULS schemes, then alpha subcycles we required, interface property we required, phase change mixture we required. Okay, this because now we have a volumetric source terms, so FV options we required. Okay, to enable the other type of the source term, and then we have this is current number. Okay, this is what we have here, and then here we have a few things like alpha control. Okay, and then we have alpha subcycle. Okay, and then we have a U equation. So if you look at from here, in here we have this number of entries. Okay, and in this we have this file. So idea is that we try to remove this file and try to add up these quantities from here. Appropriately we supposed to take into account few change in the U equation. So if you look at the U equation for this, we come to know that because now we have a interface, and based on that we have a surface tension, all this quantity we supposed to activate in the U equations. Okay, so same way if you look at the U equation of cavitation form, that entries is missing. Okay, and so what we do, we try to add up the U equation from this area and plug it there. In the similar line, if you look at the P equation from interface change, okay, it is different as compared to the P equation from the cavity form. Okay, because compressibility and all this concept is there. Okay, so what we do, we try to remove this particular P equations and try to straight away copy everything from the interface change. Okay, so that is the few change we going to do or adapt when we going to develop this particular solver. Okay, so that is what about the interface change solver. Okay, Now idea is that we have to add up the cavity form, okay, and then what we do, we try to modify the cavity form for our requirement, and then we try to generate our new solver. Okay, so that is the basic idea. So let's try to do that. Okay, so first copy the cavity form. Okay, so let me first clean this area. Okay, so idea is that first add up the cavity form from the our installed version. So let's add up this cavity form, copy into our area code. Okay, paste it, and we try to give the name as a cavity transport form. Okay, so that is the name of our solver that we want to give. I give 001. Wait a minute. Okay, and cavity transport form, that is the name I want to add up. Similar line, straight away change the name to our .c file. Okay, so first we are just generating the template. So C file is modified. This is not required, so just delete that part. Now open this both the files. Okay, and here also we want cavity transport form, and make sure it's supposed to go into the user. Okay, so before we further modify, let's make sure that everything is correct. So simply just compile this particular solver. So f3.0 wclean.all, okay, and then wmac. So first we simply compile the solver, okay, without any modification. So we sure that whatever we fetch from the application area, it's correct outside. Okay, so now our this particular template is ready. Now let's start exploring how to modify this particular solver. Okay, so for that let's open this cavitation form file. Okay, so this file we want to look at. Okay, and idea is that we try to explore, or we try to add up certain phase change. So sorry, from interface change form we try to add up this two phase mixture models. Okay, so where that exactly available, just have an idea. So if you look at in the phase change model, okay, here we have phase change to phase mixture, and this is the Kunz model available. So we try to copy this entire of this file, directory. Okay, why we are copying? Because we want to adapt this particular model that is not available inside the cavitation form. So idea is that we try to, from the cavitation form, we try to remove this barometric equation and vapor mass fractions and compressibility related part, and instead of that we try to add up this transport equations inside the cavitation form. So when we need to import this transport equation, we require the evaporation and condensation source term. For that we use the Kunz model, and for that we require this phase change mixture model. So I am adapting this phase change mixture model from the interface change form and simply copying here. Later on we will link. Okay, so just whatever required we are copying from the respective directory. Okay, what else we needed? If you look at the equations, okay, so for this equation we require the alpha equation supposed to be solved. Okay, so that is the alpha equation supposed to be solved. So relatively couple of the files we have to copy from this area as well. So we require alpha control. Okay, then we required alpha equation and alpha subcycles. Okay, so couple of the files that is needed from this area, and we supposed to copy this couple of the files from this area to our area. Okay, so what alpha control, I think okay, if later on needed we try to add up, but these two equation definitely we needed. So let me copy this both the equation into this area. Okay, so this two equation needed. Along with that we don't require now alpha psi.h, so let me delete these files. Okay, straight away we are not needed, so I am removing this file. So whatever I want to remove, it is better to have a backup of it. Okay, so what I supposed to do, I say that I will remove. Okay, so I constructed that one folder. Okay, so whatever I am deleting, I am keeping in this dump folder. So if required, later on we take this thing again. So psi, alpha psi, no more required. Okay, continuity error check, no more required. Okay, then what else? Read thermophysical properties, I think not required. Okay, set delta, all these things no more required. Okay, so because that thing is not here, look, that's why I'm removing. Okay, so we are adapting certain things from here, so whatever not needed, we simply then create control.h. so let me see, acoustic current number, I think that is also not required at present. So later on if we required, then we try to adapt. Okay, so I'm deleting that part. Read control, I think not required, let's delete it. Row equations is the same equation what we are solving, so let keep that equations. Okay, so that many files at present I removed from our main area. Later on if we required, we adapt that. Okay, and what I did, I try to copy this and this two file from this area. Okay, what is has a alpha control, it try to read some alpha subcycle and all these things. So mu, I think later on if we required, we try to adapt these files. So at present let's let it be like this way. Okay, so what else? Okay, so this is now transient cavitation code based on, so let me also change the descriptions, so that is better. So I am adapting the description, couple of things here for incompressible. Okay, transient cavitation code based on two phase change model. Okay, based on phase change model, that is based on phase change model. Okay, for which the and turbulence is unable. What else we have? Transient cavitation model, but this transient cavitation model for incompressible fluid. Okay, so transient cavitation model for incompressible fluid. Okay, based on phase change models. Okay, so that is what we have a description for this. Now let's first remove what is not needed. Okay, from this area. So what is not needed, definitely this so first comment it. Okay, so barometric compressibility models not required, definitely. Okay, incompressible two phase mixture, so let's see here, incompressible two phase mixture is not required, but we require the two phase mixture. Turbulent this is required. So now let's few things add up from this area. So all these things we required from here to this area. Okay, so let's try to add up couple of things. MULES subcycle interface property phase change turbulence model is here, so let's delete that. Okay, pimple control is also there, so let's delete that pimple control. Then FV list and fixed this two things, so if required, but I'm keeping after this. Okay, so what I did, I adapted couple of the files from this phase change area. Okay, in the similar line, let's compare this few entries from here. So we have a set root, create time, this mesh. Okay, then this read property no more required. Okay, create control not required, create field required, current number required. Okay, and then set initial delta t, I think not required, it's required, no worry. So let me add up few things from this area and try to compare what we have. So create field, FV options, time control, current number. Okay, then then we have initial this thing. So let me comment everything and let's add up from that area only. Okay, if it creates some error, then we come back. Okay, so this is the few things we adapted. Okay, so and few things we removed. So whatever is not needed, idea is that we try to remove that part. Okay, now what else? If you look at inside of this, then we have this two entry that will take care of the compressibility effect. So in place of this, what we going to do, we try to add up few things from this area. So we say let's include alpha control. Okay, then alpha control till this we required, till u equation dot h, whatever we have, we try to add up this all the entries. Okay, so here we have alpha control, so definitely alpha control is file we needed. So let me add up from this to this area. Okay, so alpha control we needed, so these files we removed. Okay, now alpha subcycle, I think that is fine. Okay, what else? So this things we adapted in the .c file. Okay, so now let's look at the few things from the create field area. So let's go to the create field area from this. So create field, inside the create field, whatever is not needed, okay, so we try to remove that. So reading the transport property about this alpha mixture and all these things. Okay, so let me see, create field, fine. So reading the transport property mixture, now this mixture and alpha V and alpha L, liquid and vapor, not required. So let me comment this area. Okay, alpha mixture, compressibility, all these things no more be required till this. Okay, so I am commenting up to this area. Okay, so what I retain the P, rho, U. Okay, then create field anyway required, then rho and phi is required because that is also be there, and then we have a mesh set of flux. Okay, now if we look at the create field file from the interface change form, so let's add a few things from there. So first of all, in case of the pressure, we are reading the P rho gh. Okay, so P is calculated previously based on the compressibility model. Okay, now here we have a hydrostatic pressure we supposed to define. Okay, so what we supposed to do, we try to add up these lines from this area. Okay, and wherever we have pressure, we try to comment the pressure. Okay, and add up this new entry. Okay, so what I did, I commented the pressure. Okay, and in case of that, now we are reading the P rho gh. Okay, so when we commented the pressure, okay, but how the pressure is built up in the this phase change model, just look at, so somewhere entry about the pressure is definitely there. Okay, so it is here. So what we supposed to do, we try to add up from here everything. Okay, whatever we needed till the last line. Okay, so here first understand, we create the volume pressure field from the hydrostatic pressure, we define the reference values. Okay, wherever needed. Okay, so this is all about that. Okay, and then we ask the set flux required for alpha and the this pressure, so that entry we required. So let's add up from this area. Okay, copy into our area at the end only. After this turbulence model, we try to add up that. Okay, so this is the few entry we adapted from this area, so that here also is this thing. Okay, now so we are set with this pressure what we modified. Okay, so we adapted the pressure very neatly. Then what else, just check the rho, because if you look at this create field file, we change the rho. Okay, so let's see, rho is here. Okay, So in the compressibility we try to modify the row by this way. So that means we have to change the definition of row depending on the how we able to adapt here. But before just look at if you want to create the row, we required what? Create phase change property. So in case of the transport property, let's create the phase change property, okay, and depending on that phase change property we able to create the row. So that is the idea. So here let's adapt the phase change property, okay, and depending on the phase change property we try to adapt the row. Now no more pressure this required, flux required for pressure is not required because now we have a hydrostatic pressure, and this row is also no more required because we changing the definition of row, okay. So here we have pressure U, then rho phi. Until unless we have row we cannot construct this, so this entry is supposed to go after the our row creations, okay. So after this row we created, we supposed to have a rho phi entry because row is needed inside the rho phi, okay. So I just rearrange this entry from this area, okay. So with this what happened, we able to manage the this entire files related to the interface change. So what change we made? We delete the pressure. In case of the pressure we add up the hydrostatic pressure, and then we delete the all the entries related to the this compressibility and the row from the this cavitation form, and we adapted the entry from the phase change. So phase change to phase mixture model, based on that we try to adapt this, okay. So phase change mixture models we are creating here, okay. Auto create phase change mixture model, okay. So let's see, I didn't miss anything, okay. Phase change mixture model we adapted, fine, okay. So that is needed, otherwise we not able to see the phase change model. Then definition of row we now change, okay, and then row phi is the same. Then we construct the interface alpha property, okay. This is turbulence. We change the style for pressure, okay. So from the hydrostatic pressure we are recovering the pressure, okay, and set flux required is previously for pressure, now it is not for pressure but it is for the hydrostatic pressure, okay. So that is the few changes we made inside this particular .c files, okay. Now what else we supposed to do? So now before, because look, if we try straight away go for compilation, it definitely going to show us some error, okay. It says that this phase change mixture.h file is not available because we didn't compile that phase change mixture model inside of it. So let's first compile this phase change model. So let's go here, this we adapted from this phase change along with this all copy. We also copy this phase change to phase mixture, this file. So let's go to that file, just delete few more models that is not needed. So I'm deleting this, but I have to retain this phase change to phase mixture model and Kunj model, and then look at the make file, okay. So in the make file appropriately we supposed to change few things. So phase change required, this required, this is no more required, okay. Then it's supposed to go into the user lib bin, okay. So now first let's compile this phase change model, and then we try to link this phase change model inside of our area, okay. So that is the idea. Then what change we supposed to do? So this is what needed. Along with that, this options files, okay, we supposed to go for a local local adaptation of the different libraries. So in the lib these files we supposed to go for this one entry form, okay, user lib bin, okay. That is needed because whatever is available locally we supposed to adapt this entry here, okay. what else, anything needed? I think no. So first let's compile this and check that either that phase change model is compiled or not. So cd phase change. So before the solver compilation, whatever the dependent library we are compiling, okay, and this is not the executable, this is the dynamically linkable library. So libso. So our library is ready. Okay, so we set the library. So now we are set for compilation, but now we have to link this library inside our solver. Okay, so let's go back to our solver area, and here inside the options we have to change couple of the things like barometric compressibility modeling, no more required. Okay, so let's delete that part. Okay, along with that, in case of that, what we supposed to do, the way it is linked in the interface change form, similar way we have to add up that library. So go to interface change make folder option file. So here look, they included like this way. So let's add up the similar line, this entry from this area to our area. Okay, so we adopted this phase change mixture model. Okay, so it is available inside of it. Along with that, what's needed, we also supposed to incorporate this L phase change to mixture model, this library from this area. Okay, okay, along with that, few more entries here also we needed. Let's see, this FV options not available. Okay, so FV tool options, if not there, we supposed to add a tool there, but FV options is not there. Okay, so let's add up this from this area. Okay, so FV options required. Okay, along with the FV options, we also required here L2 two-phase mixture, the two-phase property is there. Sorry. So here we have a turbulence incompressible barometric, this is no more needed. So let's delete that entry from this area. Okay, this is not needed. Incompressible turbulence model, fine. Along with that, what we supposed to have, we supposed to have this two-phase change library. Okay, along with that, for FV options we must have this library as well. Okay, so that is the two important thing we supposed to have. Okay, and if we require some sampling also, then add up this sampling as well. Okay, so I am adapting this, let's say, sampling as well. Okay, along with that, so we have a sampling options. So I adapted a sampling from here, so make sure I also have a sampling from this area as well. Okay, so sampling is there. Okay, so we have a sampling and all these entries we have here. Okay, so sampling I adapted. Okay, now what to do, let's try to compile it and have an idea what error we are getting. Okay, so let's see. So let's come out of it. Read control.h, no file or directory. So in the cavity transport 75 number lines we have few things. So let's see what we have. Read control, so have an idea. In the this we have a create control. In case of this we have a create control, no more read control. Okay, so what we have create control coordinate number set delta t. So create control is no more required. So let's comment that entry. So if we compile it, we will get a till this error alpha psi dot h is till available inside the p equation. That is correct, because we yet to finalize the equations, okay, for u and p equations. So let's try to explore that part as well. So as far as the u equation is concerned, let's first fix the u equation and then we directly add up the p equations. Okay, so let's look at the u equation, how it look like. So u equation for cavity transport form is something like this way, and for interface change form, if you look at the u equations, it's something like this way. So but we have to add up these equations. Okay, so let's simply copy u equation from phase change model and paste it here. So we are set with this u equations. In the similar line, also open the p equations, okay, from both the area, so from interface change and this. But what if you look at the present p equations, we are still using the this psi and everything. Okay, so like psi alpha v psi and all, but we now change the entire solver that is not depend on the psi. So straight away we add up the p equation that is available inside the this interface change form and directly copy here. Okay, so I simply copied all the content in the p equations into the our area. Okay, so with the help of that, I able to fix the u and p equation that is needed for our requirement. Okay, so that is what we fix. Now let's try to compile it again. Okay. So I think it's going to compile without any error. Okay, so we are set with this solver creations. So what we did, we adapted the solver. Okay, let me one more time open the our file. Okay, so what we did, we look at the scalar transport form, that is what we required. Okay, so what we did is first we take into account the cavitational form. Okay, and this barometric equation of state and vapor mass fractions, we remove all that entry, but we retain the continuity and momentum equation as it is, because in the phase change form, okay, also the same equation, but here what we we want these transport equations. Okay, so that is what we added inside of this cavitation form. And for the taken into account the evaporation and condensations, we use the Cousin models, and that is available on the phase change area. So we try to add up that as inside the our code. So if you look at this part, we copied from the phase change this part and a couple of few more alpha related all the files we copied. Okay, and kept it inside the this our area. And then first we establish the library, okay, of the Cousin. Okay, so and then we compile the solver. So now the solver is ready to go. So let's now run this particular solver. Okay, so for that we required the test case, and I already have a test case. So straight away we try to look at the test case and try to run the solver. That is the idea. So test case is available here. Okay, so let's look at the test case. So let's go to the area. So open the new terminal. So it is easy. I normally do this way because in one terminal our code compilation supposed to be there, and another terminal we supposed to have our running folder. Okay, so we are set with that OF 3. Okay, so I'm in the folder. Let's first generate the mesh. Okay, now let's understand the few entry from here. So here if you look at the this transport property, turbulence property is laminar only. Okay, along with that let's look at the transport property and the G file. Okay, so inside the transport property we have water and the vapor, and we are using this phase change to phase mixture model as a Cousin. That is what we adapted inside our area. Then we set, okay, saturation pressure and surface tension we didn't take into account. Then liquid and vapor property we required, so we set here. Okay, then the few coefficients that is coming from that particular models, so that is coming from this Cousin models, so this few coefficient that is needed, so that part we set here, like CV and CC and CV. Okay, so CC and CV, then U infinity and T infinity. Okay, so U infinity that is needed. Okay, so and the T infinity that is needed. Okay, so all these things we set here. Okay, so depending on the different this particular models, we have to set these coefficients. Okay, so coefficient is set. Okay, and then we just simply have to run our solver. Okay, so everything is available as a setting point of view inside of it. Okay, so if you look at all the U file and everything, okay, so we have some internal initialized U field. Okay, and inlet is a fixed value from the internal field, so we are setting this value as it is. Okay, outlet pressure, inlet outlet we are fixing. Okay, so that part is also there. So all the entries that is relevant to for the calculation of this particular case is available. Now let's run the case, and our solver name we supposed to use this cavity transport form. Okay, so let's run this solver. Okay, so here we have this MUL schemes. Okay, that is we adapted inside the where here this one CUMU LES schemes we incorporated. Okay, so it is available. Along with that, what we are doing, we are solving for alpha water initializations. So alpha equation is solved inside the this thing, that is exactly these things happening before we start the actual U equations. Okay, so we are solving for alpha first, so that is exactly happening, and then we try to finalize the momentum equations. Okay, and then the pressure equations. Okay, so it take time. Okay, so I suggest you run for a longer enough time and then look at the progress of the simulation. But idea is that how to set up the solver, so that we explore with the help of this particular very nice test case. Okay, so idea is very simple. We adapted few equations from one solver, few equations from another solver, merge both the equations and construct the entirely new class of the solvers. Okay, so here at the beginning what we seen is that this particular cavity transport form, cavity form was compressible environment, but we want the incompressible environment cavitation form. Okay, so that's why we adapted that alpha as a transport equations, plug it here and resolve the dependencies, and all these things we try to explore with this particular tutorial.